So on to our second lecture of the week. So what we're hoping to do now is you've integrated before. You found the area under a curve, okay? So let's draw that. So I might just say, okay, I seem to have gone very flat in the lecturing. I think I'm kind of running out of all kind of energy. And I think perhaps the lectures from last year are a better job. So they are there in the summary. It's just I mightn't write exactly the same thing. So if you have your own copy of the notes, I possibly recommend using last year's videos. But if you're using the scanned version, this is the one probably to be following. Okay. So yeah, the area here, the idea is that you sum over this line. So it's like an infinite sum. It's like every point along the line segment contributes something to the sum. So you're summing over a line or an interval. So what double integration is, it's summing over a two-dimensional shape. So be clear here. So you're integrating here over this thing, and you could call this area here the integral over AB of f of x dx. Okay, so you can also sum up over a two, so that green bit on the bottom, the interval a to b, is one-dimensional. What about if we sum over a two-dimensional shape? And what would it mean? Now here you've got an area. Now if you have a function of two variables, its graph forms a surface. We would have done some of this in Math 7019. And here we have, and now that possibly goes negative, but imagine that it stays positive. So when you sum over a one-dimensional thing, you're ending up with an area, depending on what you integrate. And if you sum over a two-dimensional shape, in this case, is it a square? Looks like a square, yeah. You're ending up with a volume. Now, it's not a volume integral. Okay, we call this a double integral. We might now it's all the regions between those lines. Now this region, say we call it R. I'll just give you the notation. So you can give the x coordinates and then I don't know how that happens, the x coordinates and then the y coordinates. So see the way I did a to b there? You can do that for the x coordinates here. You can see that the x coordinates go from -2 to 2. And then if you want to give the y coordinates, you do times -2 to 2. And what you'd be integrating here is the function f of xy, and that would be a double integral. So here it would just turn out to be a volume, but don't think of it as a volume integral. You're integrating over an area. So we're talking about the integral over this rectangle f of xy. Now what you do now is it's not dx, it's dA. Okay. In this section, we're going to kind of learn how to calculate that kind of a thing. Okay, so if we define the double integral of a positive function over a rectangle in the plane, in this case, we're defining it as that volume. Okay, so how we would find that volume is we'd approximate it first using three-dimensional boxes. So I've got a picture on the next page where we're going to approximate the volume using 8 boxes. So this is a slightly different region here. So what we're doing is we're summing over this region. Now actually what we're summing up is f of xy, which is height, times area. And so that the idea actually is what you're summing up is loads of little, there, like the height by an area is a volume, so you're adding up loads of little volumes. Okay, and what we're saying back here is that if you want to approximate the volume, so that's, I don't know, can you see the shape that I'm forming here? So So there's a surface up top, it's a curvy surface, and we're looking for the volume underneath it by adding up over the region, the green region. Okay, so we'll approximate it using 8 boxes. So the volume under the surface, which we define to be this double integral. Now, okay, where is this dA is equal to dx by dy coming from? Well, we'll show you that now as well. So if you've got an x-axis and a y-axis, and say we grid it up, so the language here is mesh, and suppose the width of the mesh here is dx. Now really you're thinking of delta x, but we'll get to that. And the width of this is dy. Well, then this area dA is dx by dy. Okay, so that's where this dA is equal to dx dy is coming from. So we estimate the volume under the surface by the volume of the boxes, and we take the length and the base to be dx and dy. We'll draw that on the picture on the next page. And we'll take the centroid, which is kind of a midpoint of each of the boxes, and we'll calculate the value of the function at each of those points. So this, let's say this is the point x1, y1, star, star. Okay, this width is delta x, this width is delta y, and apologies, these should be a little, now really delta is actually more accurate, but I'm just going to go dx and dy. Okay, so say for example the first box, which is the box over in the top left hand corner. So if you throw in the point x1 star, y1 star into the function and multiply it by dx dy, you get the volume of the first box. So just to get our notation in a row, we'll go back. Yeah, so v of box 1 is equal to the height, which is this number, by the area, which is, now I'm just going to write dA here, but really it should be dA is dx by dy. Okay, so you add them all up. Now what you want now is not just 8 boxes, but a general number of boxes. And as you get, so similar to before, as you take more and more and more boxes, the dx slash dy, and actually here I can see I was right the first time. So this is like delta x, this is like delta y. And what happens if you take more and more and more boxes? The delta x gets really, really small like dx. The delta y gets really, really small like dy. And you can show that the approximations get better and better and better. And so what you do is you take the number of boxes to infinity and you get, this is the definition of a double integral. Now, there's 2 ways you can write this double integral. If you kind of specify that the region is 2-dimensional, like say we say that it's, or we're adding up over some kind of a box, 2-dimensional box, you can say that. Or if you want, you can write it twice to signify that actually to calculate it, there's 2 antiderivatives. But both of them are actually, like it depends on what you think about integration. So if integration to you really just means the opposite of differentiation, you'd use the second one. So you need to anti-differentiate twice to calculate one of these. Whereas if you think about integration as a sum, you only need one of them, but you can use either, they're okay. Okay, now recall that it's difficult to calculate integrals directly. We use the fundamental theorem of calculus, and the fundamental theorem of calculus says for a normal integral over an interval AB, how do you calculate it? Well, you anti-differentiate, so you go from the derivative to the original function, and then you do top limit minus bottom limit. Now, calculating a double integral from first principles is really, really difficult as well, but it turns out that a double integral can be written as what's called a kind of an iterated integral. So you can do it in kind of 2 steps, as we'll explain. Okay. So take your region. Now, what kind of a region we're going to look at here? Yeah, we're going to look at a rectangular region here. Now, what you have to kind of do now is kind of forget about the volume, and you're just adding up over this region here. Okay, so this is A, this is B, and we're saying that this is C, and this is D. Okay, now we're going to be doing some meshing, which I haven't done. So let's take these lines out, and let's do a mesh. So mesh means you write it, basically you'll see what I mean. Now the finer that you do this, the more it makes sense as such. But for ease of actually expressing what we're doing, well, we won't mesh it up completely actually. So yeah, okay. So actually you imagine that there's infinitely many of these vertical lines, and similar story. Actually I don't want that. Okay, so take these vertical lines and you imagine that they're very, 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 very thin. So the width of these is just dx. Okay. And what we're going to do is first, so you're summing up over this rectangle. Oh, we might as well write down something as well. So this rectangle, well, actually, I like the symbol box. So this is, what are the x coordinates? A to B times the y coordinates C to D. Okay. So you're trying to add up over this 2-dimensional shape. So what you can do is you can find the contribution to the sum from a single strip. Now at this single strip, notice that x is constant. So this is a little bit like, it should remind you a little bit of partial differentiation. Okay. Now y is changing along that strip. So let's see, so fix a value of x between a and b, we've done that, and a width dx, we've done that. Now add up the contribution to the sum as you go from here, which is y equal to c, up to here at y equal to d. Okay, so this would be, you'll be adding up. Now we'll talk about why the dx comes out in a second. So what are we actually adding up here? So you're adding up over the whole rectangle f of xy by dA, which is the same as dx dy. Okay, so along this strip, the width dx is constant, so that can come out. So all you have to do is add up f of xy dy from y equal to c to y equal to d, but that's actually equal just to a normal integral because x is constant. So this is just an ordinary integral. It looks a bit funny, but it is an ordinary integral, which we'll be able to go at in examples quite soon. Now what you can do is, that's the contribution to the sum from a single strip. And now what you have to do is add up the contributions of all the strips. So add up from x equal to a all the way across to x equal to b. Now, because dx is essentially infinitely small, there's infinitely many of these strips. They're infinitely many small, and of course, when you're adding up infinitely many, infinitely small things, it's an integral. And I suppose that's where this integral here is coming from, because f of x, y, dx, dy is infinitely small, and you're adding up loads of them. Okay, so if you want to then do the integral over the entire box, you'll add up the contribution from the strip at x, but each of those contributions is very, very small, so it becomes an integral. You can also do it the other way around. You can fix y, and so you can sum vertically and then horizontally, or horizontally and then vertically. Okay, I think we're going to see some examples. or applications. Now, there's a thing here. As the mesh gets very fine, it turns into a fiber. So what I'm saying is, so a mesh would look something like this. And if you do really, really fine, like infinitely fine, it's more like a fiber. It's the kind of idea there. Okay. So let's explain this. So if rho is the mass per unit area, then integrating over a lamina R, rho dA, is the same as adding up rho delta A, roughly. And if rho is mass per unit area, then the mass per unit area times area will be mass. So you're adding up little bits of mass, you get the full mass. So let's kind of explain this a little bit. Okay, so we have some kind of a lamina. Now a lamina just means something that is actually three-dimensional, but it's very, very thin. So you can treat it like a two-dimensional object. So let's look, so imagine we have a mesh. So the mesh is, we can kind of see what's going on. Okay. So this is a little bit of mass. Okay. Now this should be approximately equal to the density at the midpoint, which we'll call x star, y star, the centroid or whatever. So that's the density. That's the density per unit area. So if you multiply the density per area by the area, and we want to say that this is a width delta x, this is a width delta y, get delta x delta y. Now if you want to make that more accurate, you turn the mesh into a fiber. You take delta x, so as say delta x and delta y go to 0, which we call basically dx dy. Now if this is really bothering you that it's very imprecise, it can be made precise, but if it's really bothering you, you're kind of you might be more of a mathematician than an engineer. Okay, so this approximation gets better, and so you end up with dm is equal to rho. Now I won't write x star, I'll just write xy dx dy. So that would be the mass of, rather than this kind of square that you can see, an infinitely small square. And therefore if you add up all over the lamina all the little bits of mass, you get the total mass. So adding up infinitely many infinitely small things is integration. Similar story. Now how the hell am I going to do that? Let's be careful here, I can't really remember how I do this. Okay, so we're looking for the centroid. I think we're just going to do the x bar one. So draw some kind of a lamina, and we'll just make up a point where we think the centroid is. Let's just go for this point here. Okay, so suppose the centroid is at x bar, y bar. So the question is, how do we actually find that? So I think we're just going to look at the x bar. So what you do is you draw a line, essentially, and you take a little area over here, say. Okay, that's a little bit of area. And we're going to calculate the torque of this about that line. So this distance would be, well, if this is x, this would be x minus x bar. And so the little bit of torque, let me say, it'll be proportional to dA. The units are kind of messing around here. What are we saying? So whatever force the area elements acts about this, it'll be proportional to dA. So, like, what are we saying? So the force, the internal force, we're trying to say that it will be, it'll be to do, basically to do with the weight. the weight, which is assuming the material is homogeneous or homogeneous, however that word is said, means that really it only matters how big the bit is, and how big the bit is determined by dA. And if you double dA, you double the mass, you double the force. So that's to say that the force is proportional to dA. So the amount of torque, a little bit of torque here, will be the force, which will be k dA, by the distance x minus x bar. And what we need to do is add all those torques up over the whole region. So the total, now again, to make it more accurate, what we do is we'll take the area to be very, very small. And that's the same as going from a mesh to a fiber. And so a little bit of torque is equal to some constant, which actually ends up not being important, dA times x minus x bar. And what we have to do is add up all of the torques over the region and set that equal to 0. That's how you find a centroid, no internal torques, or the sum of the torques is 0. So that's actually what happens there. We end up with a formula for the centroid. And similarly, you can get the y coordinate. Another story is your second moment of area. So take some kind of a region, say this yoke, for argument's sake. Okay, take a small area, so that means a meshing. Okay, and the second moment of area will be the y coordinate at the midpoint. So a little bit of second moment of area from that bit will be, now the approximation is that the y coordinate isn't actually the same over the whole little bit of area. So that's why this is approximate. But you can get it more accurate if you take the mesh to get really, really fine and turn into a fiber. So you get a little bit of second moment of area is equal to y squared dA. And then as usual, you add them all up over the region, so you get the integral. So that's the second moment of area. Okay. So I think we're going to have enough to do an example, which we'll do in the next lecture.